Our group project is Quick Park. Our group number is 43. My name is Harsha Dantaluri.
My name is Liam McCluskey.
My name is Yusuf Azawad.
My name is Keith Kuchenbrod, and the advisor for our project was Professor Roy Yates.
Our project addresses the problem that drivers face when they drive into a busy parking lot and can't immediately see which spots are free and which are occupied. This results in the driver having to waste a lot of time driving around trying to find an open spot and lots of excess traffic. So there are current smart parking solutions, however, many of them use expensive equipment such as in-ground sensors, and so these solutions are not easily scalable and are not cost effective.
Similar existing solutions include TinyNode by Paradox Engineering and the Smart Park system. Both these systems utilize overhead and in-ground sensors to detect if a car is taking up a parking spot. The issues with these systems currently is that they're expensive because you have to pay for each sensor per spot. You need experts to install them into the pavement or overhead, and construction on the road will cause any delay or unavailability of the parking system. And it's not really a long-term solution because parking sensors tend to need to be replaced after a certain period of time.
So our solution in a sentence is we want to design a parking application that will provide a user with real-time occupancy data for a parking lot and be able to give the user directions to the nearest or optimal spot, where the optimal spot is defined as the spot that's closest to where they're trying to go when they exit the parking lot. So the scope of work for our project is we wanted to use Raspberry Pis to capture and send images of parking lots to an AWS server. And on the AWS server, we need to use an object detection script to generate and store occupancy data for the images received by the Raspberry Pi. And lastly, we wanted to create an iOS application to display this occupancy data in real time and provide the user with navigation to the nearest open spot. So just an overview of our system. It starts with the Raspberry Pis that we have placed in fixed positions overlooking parking lots, which we use to capture images of the parking lots and send it to the AWS server. Then on the AWS server, we process these images with an object detection script, and that generates occupancy data, which says whether each spot in the parking lot is free or occupied. And then we store this, and on the AWS server, we handle the GET requests from the iOS application. And lastly, on the iOS app, this is where we display the real-time occupancy data in an easy-to-understand format, as you can see here. Red dots correspond to occupied spots, and green dots correspond to free spots. And lastly, we want to be able to provide directions for users to the nearest or most optimal open parking spot. Now we will play the demonstration of our application. Application Quick Park, and so let's just log in as a registered user. And in addition to making this a smart parking app, we wanted to make this a general Rutgers parking application. So, for example, let's look up a destination in Rutgers. Let's look up Bush Student Center. And when I click this, it will display the location that I searched for and all of the nearby parking lots. In addition to this, I can click this button here and see all of the nearby parking lots sorted by distance from the destination I'm searching for in Rutgers. And I can click on whatever parking pass I have to see whether or not I can park there at the current moment in time. So now what we want to show is the ability of our application to show real-time occupancy data for a parking lot. So let's click lot 49, which is one of the lots that we have Raspberry Pis installed in to capture images. So let's click this. and when I click it, it just shows a blank image of the structure of the parking lot. But when I click refresh, it will show the real-time occupancy data of the parking lot, where red dots are occupied spots and green spots are free spots. So if you look to the left over here, these are the images that are being sent on a loop to the AWS server to be processed. So as you can see, this image is the top left portion of the lot here. So this occupied spot corresponds to this car. This image here is the bottom right portion of this image. So there's one occupied spot here, which corresponds to this car. And similar for this image, which is the top right of this. And this image is the bottom right here. And lastly, this image corresponds to the bottom of the parking lot, so as it is occupied. And next, what we want to show is the ability of our application to show directions to the best open spot. To show the navigation aspect of our application, let's click on lot 49. And now we're going to generate random occupancy data just to show the ability of our application to draw paths to different open spots. So let's refresh the data and let's get directions. So every time I click get directions, it fetches the newest occupancy data, and as you can see here, it draws a path to the open spot that's nearest to this exit point. Let's just click it a few more times. Now this is the nearest spot. Now this. And it works, as you can see. So now I just want to show a test image to show sort of the underlying structure of how we generate this shortest path information. So what we do is we take an image of a lot, a satellite image, and then we convert it to a weighted graph like this, where there's a node within each spot, beside each spot, and at every intersection of roadways within the parking lot. So now let's generate random occupancy for this test lot, and if we refresh it, and let's get directions, let's click get directions. So as you can see, it draws a path, the shortest path to the nearest open spot. Just click it a few more times, just like this.
So for our camera setup, we used 4 main tools. To start off, we have the Raspberry Pi Model 4. This is essentially a small computer, while at the same time being pretty powerful. It has its own dedicated RAM and CPU, so you can basically do anything that you would on a regular Linux computer. It also has a lot of GPIO options. You can plug in through the GPIO pins on the top left for any sensor. But in our case, we used the Raspberry Pi camera slot and the USB ports to plug in USB cameras. It's also very cheap and easy to use. This model comes in at around $50, and there are plenty of tutorials online that will show you how to get started and build any project that you want. Furthermore, we have the Pi camera. This was a 1080p camera, so it provided us with a high resolution image of any parking lot. It was also very easily integratable with the Pi, and the main point that we wanted to use this camera was because it has a high FOV, which means that we can capture a large amount of spots with just one camera. Furthermore, we also used a cellular device. In our case, it was a cell phone that provided a hotspot for both our Raspberry Pi and a laptop that would SSH into the Pi. In a future setup, we would probably use a dedicated USB Wi-Fi dongle. The main point for this is because we don't necessarily know if the location that we'd place this setup would have access to a campus Wi-Fi such as Rutgers wireless, and it would also be pretty stable. And finally, we used OpenCV to process our images. So we had basically a video feed, and in that video feed, OpenCV separates the video feed into plenty of frames for you to manipulate and use however you want. And this was developed in Python. So how our camera setup works is essentially there is a video feed that is being displayed on our laptop screen, and this video feed is going to be separated into multiple frames by OpenCV, and you can essentially take each frame that is inside of an array, and you can manipulate it or save it however you want as a regular image. So this frame would be saved as an image in our project folder, and once it's saved, it would be sent to our EC2 instance on our AWS server through a post request, and attached to this post request would be a couple data points. These are data points that would go into our JSON file, and this would be the parking lot name, the camera name, when it was last updated, and the image name. So the reason why we have the camera name and the parking lot name is because we would have multiple parking lots and multiple cameras per parking lot. So the easiest way to differentiate this would be to send the data to the JSON file while also sending the image. So here's a quick look at our setup. On the right, we have a Raspberry Pi connected to a battery pack and a USB camera. Not shown in the image is our cell phone that provided a hotspot to the Raspberry Pi. On the left, we have our enclosure set up on top of a tripod. This allowed us to get a fixed position and a high vantage point to see the parking lots.
For the image recognition portion of our project, we utilized an open source database called pklot. Pklot contained around 700,000 parking spot images from 3 different cameras, from 3 different weather conditions, while also containing some images with obstructions. A couple steps to our data preprocessing, we made sure to sort these images into both training and testing sets. However, due to model training time taking super long for 700,000 parking spot images, we only utilized around 60,000 for our training set and around 50,000 for our test set. To ensure our model stability throughout training, we made sure to normalize our images pixel values between the values of 0 and 1. And to make sure our end model was more robust, we made sure to provide random augmentation to these training images, such as rotations, adding shears, and flipping. Moving on to what actually makes the image recognition portion of our project work is our model. Because we were dealing with a simpler classification problem of deciding whether a parking spot was free or occupied, we decided to start out with a simpler model. We first looked at the original AlexNet CNN model, which was originally 8 layers. However, we ended up using a modified version of it since it was a lot smaller. This modified version brought the number of convolutional layers down from 5 to 3 and fully connected down from 3 to 2. It also altered the filter sizes on each of the convolutional layers, which ultimately took the number of weight parameters from 46 million down to 55,000. This not only reduced the size of the model, but also reduced the complexity. One of the small changes we made to this modified AlexNet CNN model was changing the output layer's activation function from a softmax to a sigmoid function. And in doing so, we only had one output, which would output a value of between 0 and 1. If the value was closer to 0, then the prediction would deem that the spot was free, and if the output was closer to 1, then the prediction would deem that the spot was occupied. This prediction was then fed into a cross-entropy loss function, which generated our loss value. And overall, when testing this model on our test set with 50,000 images, we achieved a accuracy of 98% and a loss value of 0.037. So after getting our modified AlexNet CNN model to generate some predictions, we also had to come up with our own web server. And we did this using 4 things. We first created our Amazon Web Service EC2 instance, and then in this instance, we installed our Nginx HTTP web server, we installed our uWhiskey application server, and we also set up our Flask application within our server. And before I talk about the scripts, I'm just going to talk about how in general this whole server would work with just a request. So our client will send a request to our Nginx server. Our Nginx server will act as a reverse proxy and forward this request to our application uWhiskey application server via a socket. And then our uWhiskey application server will then call a Flask object to handle this request. And then our Flask object will create a response appropriate for that request and send it back. And currently, we have 3 scripts on our server working. So our first script we have is to handle all the post requests from all the cameras sending images from the lots. The script will then save these images into a folder. Moving on to our second script is our prediction script. This script will then take the image, the newly set image, and the newly saved image, and then run a prediction on it, and then update our JSON file for that specific parking lot with the appropriate parking spot statuses. And then lastly, the last script we have is to handle all the GET requests from our iOS app to the server. And so the iOS app would send a GET request, our server would respond with the information within that parking lot's JSON file, and that's it. And so if you would like to see all the structure that we use to send information from our server to our application, you can click this link below. This is just a live feed of our server sending information.
If we had more time, these are things we would like to continue working on. First is the RISE CNN model to improve image recognition accuracy, thus increasing the accuracy of our prediction model. Second is to create a housing unit for our camera, thus weatherproofing the system and creating a permanent housing unit for our camera setup. Lastly is to create and run more test units so we're able to do more live testing in live parking lots with more traffic.